Today, I'll be proving that if a quadrilateral with side lengths A, B, C, D has both circumscribed and inscribed circles, then its area is equal to the square root of A, B, C, D. So I'll start by drawing out the quadrilateral. Okay, so we have A, B, C, and D. Now I'll draw the inscribed circle. So the inscribed circle is tangent to the four sides of the quadrilateral. Okay. So this is not the most accurate diagram, but it should suffice for this problem. Okay. And now let's draw the center I of this inscribed circle. Now we have the radii are perpendicular to the tangents. And we will make the tangency points E, F, G, and H. Okay. Now we'll make the length AE equal to X. Since we have two equal tangents, AE and AH, then AH is also equal to X. We also have, if we let DH equal to Y, then DG is an equal tangent to DH, so it's also Y. If we make CG equal to Z, then CF is equal to CG, and it's also Z. And if you make BE equal to T, we'll have BF and BT are both T. Okay. Now we will let the angle BIE equal to alpha. Then, since triangles BIE and BIF are congruent, because we have equal radii, we have equal radii IE, IF, IG, and IH. So right angle triangles IEB and IFB are congruent. So we have two angles equal to alpha. Okay. Now if you look on the other side, we'll use the fact that ABCD is cyclic. So ABCD, you can draw a circle containing all four vertices. Okay, my pen was acting up just then, so I'll just remove that. Okay. So I'll just continue drawing the rest of the circle. Okay. Now, since ABCD is a cyclic quadrilateral, we have the opposite angles ABC, the opposite angles ABC and ADC are supplementary, so they add up to 180 degrees. This means we have ABC is equal to 2 alpha, and we add ADC, and we get 180 degrees. So ADC is equal to 180 degrees minus 2 alpha. So ADC is 180 degrees minus 2 alpha. And using similar reasoning to proving these two alphas are equal, we get the angle HDI is the same as the angle IDG. So it turns out that HDI and IDG will be equal to half of 180 minus 2 alpha. So it's equal to 90 minus alpha. We'll have two angles equal to 90 degrees minus alpha. So then we'll get this angle HID is alpha, and the angle DIG is equal to alpha. Okay. Now we can see, if you have a look at the triangles DHI, it turns out that DHI is similar to triangle DHI over here. DHI is similar to triangle IEB. And this is because we have the angle alpha here in DHI and the angle alpha here in IEB. So we have two similar right angle triangles. Now, if we make the radius of the in-circle R, so this is the inscribed circle, we have the following ratio. So using the similar triangles, we have equal ratios. The equal ratios are DH divided by HI is equal to IE divided by EB. And from here, we get Y divided by R is equal to R divided by T. And now we have R squared is equal to YT. And therefore, we have R is equal to the square root of YT. Okay, so the radius is equal to the square root of YT. Now, using symmetry and similar logic, we can also prove, we also get the radius R is equal to the square root of x, z. And this is using similar logic and using symmetry in the logic we've done with the similar triangles. Now we have R is equal to the square root of xz, and R is also equal to the square root of yt. Okay, now we will find the area of the quadrilateral. What we can see is the area. So I use two vertical bars to represent area. The area of DIC is equal to half times the base times the height. So we have the height is R, and the base is Y plus Z. Okay, and using similar logic, we can also calculate the areas of the remaining quadrilaterals. So the area of BIC is equal to half RT plus Z. The area of AIB is equal to half R of X plus T. And finally, the area of triangle AID is equal to half R times X plus Y. Okay, now we can see if we add the areas of these four triangles together, okay, sorry about that. My pen was acting up again. Okay, if we add the areas of these four triangles, we'll get the area of the quadrilateral ABCD. So if we add the areas of the four triangles, which are half RY plus Z and half RZ plus T plus Z, half RX plus T and half RX plus Y, we'll get the area of the whole quadrilateral. So the area of ABCD is equal to half Y plus Z plus T plus Z plus X plus T plus X plus Y. And this is equal to half 2x plus 2y plus 2z plus 2t. This is equal to r times x plus y plus z plus t. Okay, now going back over here, we have the square root of xz and the square root of yt is equal to r. This also means xz is equal to yt. This means x is equal to yt divided by z. So what we can do is replace every instance of x with yt divided by z. And also, you'll let r be replaced by the square root of yt. Okay, so in this area formula, we'll write r as equal to the square root of yt and x as equal to yt over z. So now we will have this as our area of the quadrilateral, and we can take a factor of 1 over z out. Okay, and we'll get this. This factorizes into z plus t y plus z. Okay, now we'll calculate the square root of the product of the four sides. So we'll calculate the square root of the product of these four sides. And we'll check that the square root of the product of the four sides is equal to this, which is the area of the quadrilateral. Okay, so the square root of the product of the four sides is we'll have the square root of x plus t times the square root of t plus z times the square root of z plus y times the square root of y plus x. Okay, so this is because the four sides are x plus t, t plus z, z plus y, and y plus x. Now we will just replace x with yt over z. And now we can take this factor of 1 over z and a factor of 1 over z here out. And since it's a square root, we'll have 1 over z out at the front, and we'll have yt plus zt, t plus z, y plus t. And here we'll have yz plus yt. Okay, now we can take a factor of t out here and a factor of y out here. And we'll have the square root of yt divided by z times the square root of y plus z, t plus z, y plus t, and z plus t. Okay. And since y plus z appears twice, okay, hang on, it should say y plus z over here. Okay, that's a correction. Okay, so since y plus z appears twice, and since z plus t appears twice, we'll have the square root is equal to just y plus z times z plus t. Okay, and this expression is equal to the expression for the quadrilateral which we found earlier. This proves that the area of the quadrilateral is the square root of the product of its side lengths. So that finishes off the proof. So hope you enjoyed this video. Thanks for watching, and I'll see you next time.